Welcome to this explainer on behalf of Forge College. I'm your host and, well, your chief engineer for today's session. We are setting the stage to build something I know you've been asking for, the ultimate permit machine blueprint, right here on Solana. Now, if you caught our last session, permit-based approvals on Solana, motivation, and EIP 2612 comparison, you already know exactly why we desperately want these gasless approvals. But today we're grabbing our hard hats, maybe some metaphorical duct tape, and we're actually translating that gasless magic into a sleek, high-performance Solana architecture. Let's get into it. Okay, here's our blueprint for today. First, designing the permit schema. Second, off-chain signature assembly. Third, the on-chain verification engine. Fourth, we'll run a system stress test. And finally, we'll wrap it up with our conclusion. So we already know exactly why we need a permit, right? We want that perfectly frictionless, gasless user experience, the kind where someone can authorize a transaction without spending their precious SOL on gas fees, because honestly, nobody likes paying the toll troll. But now we have to ask the really practical engineering question. How do we actually build this cryptographic VIP pass on Solana? How do we make sure it's secure, completely tamper-proof, and fits perfectly into the Solana programming model? Well, let's find out.
Starting us off with Phase 1, designing the permit schema.
Okay, so these 5 specific fields, they act as the structural DNA of our permit. Think of them as the 5 vital questions any bouncer at a club needs answered before letting you in. First, we have the owner, who is actually issuing this pass. Second, the delegate, who is allowed to use it. Third, the amount, how much are they allowed to spend or move around. Fourth, the nonce. This is a unique counter to make sure this exact pass can't be, photocopied and used twice. And finally, the deadline. At what exact Unix timestamp does this VIP pass turn back into a pumpkin? Every single one of these fields is strictly required to ensure absolute security and prevent replay attacks. And this brings us to what I like to call our golden rule for this entire build, canonical serialization. I know, it sounds like a massive mouthful, but it literally just means that both sides of our machine, the TypeScript client and the Rust program, must read the blueprint exactly the same way, down to the absolute byte. For Solana, we achieve this by using exactly 32 bytes for our public keys and strict little endian encoding for our numbers. Seriously, if your client writes a number left to right, but the program reads it right to left, your signature is going to fail every single time. Strict agreement is the only way this works.
Moving right along to Phase 2, off-chain signature assembly.
Now notice the really stark contrast between our two environments here. Off-chain, we're using TypeScript, tweetnacl for cryptography, and the user's key pairs. This side is incredibly fast, local, and totally free of gas. On-chain, however, we're operating in Rust, using Solana's system variables and returning strict program results. Our main job here is to build a perfect bridge between these two vastly different worlds without anything falling into the lava below. So how exactly do we build that bridge? Well, by using tweetnacl. Our off-chain client takes those carefully arranged little endian bytes we talked about and signs them using the owner's secret key. This spits out a raw 64-byte detached ED25519 signature. Think of it like stamping the serialized data with invisible cryptographic ink. It's totally off-chain, it's totally free, and it is entirely secure. The relayer will eventually pick up this signature and carry it over to the blockchain.
All right, on to Phase 3, the on-chain verification engine.
So once we're on-chain, our program executes a super strict 3-step quality control process to guarantee the VIP pass is actually legitimate. First, it has to find the signature verification. Second, it has to verify the constraints, basically checking that the pass isn't expired and hasn't been used yet. And third, it has to immediately punch the ticket by updating the nonce so it can never, ever be used again. Let's break down how it actually pulls this off. Now, this is where Solana gets wonderfully unique. Since Solana programs can't just arbitrarily call complex cryptographic primitives on their own without burning massive amounts of compute, we ingeniously inspect what's called the instructions sysvar. Think of the transaction as an airplane. Our program basically looks at the passenger manifest, that instruction sysvar, to ensure that the relayer actually brought the official ED25519 system instruction along for the ride. If it finds that verification instruction, and the payload perfectly matches our owner and our canonical bytes, boom, the signature is deemed valid. Once that signature is verified, we move straight to the state changes. To prevent any nasty race conditions, we store exactly one simple U64 nonce in a dedicated, extremely small account per owner. You might be wondering, why just one number? Well, for beautifully straightforward atomicity. By isolating this counter, we minimize rent costs and friction, ensuring that the very second a permit is used, this number ticks up by 1, permanently invalidating the previous permit. It's clean, simple, and secure. Let's put this to the test. Phase 4, System Stress Test. Okay, the really crucial point here is this matrix. We are pitting our verification engine against 3 specific archetypes: the good user, the sneaky hacker, and the time traveler. Let's see how our engine reacts to each one of them. First up, we have the good user. They do everything right. They submit a perfectly valid, correctly serialized permit with a deadline that's safely in the future. Our engine inspects the sysvar, verifies the ED2515 signature, checks the timeline, and returns a glorious OK. The VIP pass gets punched, and that stored nonce account atomically increments from 0 to 1. The requested action, like a token transfer, proceeds smoothly, exactly as intended. Next up is the sneaky hacker. Now, they intercept a valid permit, but they try to alter a single byte. Maybe they're trying to change the allowed amount from, say, 10 tokens to 10,000. Nice try, buddy. But when the transaction hits our Rust program, the sysvar check catches the canonical mismatch. The recomputed bytes on chain just don't match the signature provided, so the transaction violently fails with an error, the operation is completely halted, and most importantly, the user's nonce remains safely sitting at 0. Finally, we have the time traveler. This is your classic replay attack. They take the exact same valid permit that the good user already successfully used, and they just try to submit it again. Now, the signature is technically valid, but the scanner checks the on-chain nonce account. The permit says nonce 0, but our on-chain account was already incremented to 1. So the scanner rejects the reused nonce, the transaction fails with an invalid data error, and the user's state is perfectly protected.
Which brings us to phase 5, conclusion and next steps.
Look, if you remember only one thing from today's explainer, please let it be this quote right here. In Web3 engineering, high-level architectural flaws are honestly pretty rare. It's the encoding mismatches that will keep you up at 3 a.m. crying into your keyboard. I'm serious. If your TypeScript client and your Rust program disagree on even a single bytes order, your perfectly valid signatures are going to be rejected. You have to treat your canonical serialization as an unbreakable contract. So you now have the exact mechanics to pull this off. You structure your schema canonically, you assemble the ED2559 signature off-chain, you pass it to a relayer which packs it into a transaction so your Rust program can verify the sysvar, and finally, you update the nonce atomically in a dedicated account. Boom! That is the complete lifecycle of a secure Solana permit. So, with the verifier function humming perfectly and passing all of our stress tests, the next logical step is connecting this into a real client and relayer flow. In our next module, we're going to take this exact engine and put it inside a beautifully designed user interface to get that magical, completely invisible, gasless experience. On behalf of Forge College, thank you so much for joining me in this engineering workshop. Make sure you visit forge.college to expand your Web3 toolkit, check out the code snippets from today's lesson, and tackle the next module in the EVM to SVM track. But before you go, ask yourself this. If we can make transaction approvals completely gasless, what other Web3 frictions could we just entirely engineer out of existence? Think about it. Keep building, and I'll see you next time.